Hello everyone, welcome back to the lecture on Applied Electromagnetic Theory. We'll be continuing with the Module 4 on transmission lines. Myself, Shyama Srikumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. In the previous lectures, we have discussed on the basics of transmission lines, the transmission line equations, the solution to transmission line equations, and we learned two special types of transmission lines, namely lossless transmission lines and distortionless transmission lines. In this lecture, we'll be seeing what will be the input impedance of a transmission line, also about the parameters, reflection coefficient, and standing wave ratio. So when you consider input impedance of a transmission line, you know that impedance means it is a ratio of voltage to current. So input impedance means it is a ratio of voltage at the input end to the current at the input end. So here we are considering a transmission line which is of length L and it is having the parameters propagation constant gamma and characteristic impedance Z0. This transmission line, the left end is connected to the generator with voltage Vg and the internal generator impedance is given by Zg, and the right side is terminated by a load ZL and the voltage across the load is VL and current through the load is IL. Our aim is to calculate the impedance by looking into the transmission line at the point Z equal to 0. So here we are having the assumption that is total length is L and the voltage across this end will be V0. That is, after getting a voltage drop across Zg, the remaining voltage will be dropped across the transmission line which is given by V0. Our aim is to calculate the value of Zn. We have already determined the expression for voltage and current from the transmission line equations, and we got it as Vs of Z is equal to V0 plus e raised to minus gamma Z plus V0 minus e raised to gamma Z, and we got the expression for current as Is of Z equal to I0 plus e raised to gamma Z plus I0 minus e raised to gamma Z. Now this current can also be expressed in terms of voltage and characteristic impedance. As you all know, characteristic impedance Z0 is V0 plus by I0 plus, and that is equal to minus V0 minus by I0 minus. By incorporating this equation into the current expression, we will get Is of Z as V0 plus by Z0 e raised to gamma Z minus V0 minus by Z0 e raised to gamma Z. So this is the expression for voltage and current at any point Z on the transmission line. Our aim is to calculate the input impedance. So when you observe the value at the input end of the transmission line, the value of Z is equal to 0. So the expression for input impedance is given by Zn is equal to Vs at Z equal to 0 by Is at Z equal to 0. That is, we should divide the voltage and current at the point Z equal to 0. So when you substitute Z equal to 0, the expression for voltage becomes V0 plus V0 minus. And the expression for current becomes V0 plus minus V0 minus by Z0. So we have got an expression for Zn in terms of voltage and characteristic impedance. So we will get Zn is equal to, when we take the Z0 to the numerator, it will become Z0 into V0 plus V0 minus by V0 plus minus V0 minus. So here we are going to substitute V in terms of the impedance. So we can get the expression for Zn. So for that we are taking the voltage and current at the load end. So when you substitute Z equal to L, we will get the voltage and current across the load. So voltage across the load is VL. So when you substitute Z equal to L, you will get VL equal to V0 plus e raised to minus gamma L plus V0 minus e raised to gamma L. And the current through the load is given by IL, which is V0 plus by Z0 e raised to minus gamma L minus V0 minus by Z0 e raised to gamma L. When you take this Z0 to the LHS, you will get IL into Z0 equal to V0 plus e raised to minus gamma L minus V0 minus e raised to gamma L. So here we are having two equations. So if you add and subtract them, we will get V0 plus and V0 minus in terms of VL, IL and Z0, so that we can substitute it back here. So we are going to add these two equations as well as subtract these two equations. Hence, on solving, we will get V naught plus and V naught minus. On solving the two equations, we will get V naught plus equal to VL plus IL Z naught by 2 e raised to gamma L, and V naught minus is VL minus IL Z naught by 2 e raised to minus gamma L. We are substituting back into the expression for Zn. So when you substitute it back, you will get the expression like this. That is, we substituted here V naught plus, here it is V naught minus, again same in the denominator. Now what we are going to do is that we are going to group the terms such that we'll take VL by 2 outside. So inside it will come as e raised to gamma L plus e raised to minus gamma L. From the second term we'll take IL Z0 by 2 outside. So what is remaining is e raised to gamma L minus e raised to gamma L. Similarly in the denominator also we can take VL by 2 and IL by Z0 by 2 outside and keep the other terms inside. So then we'll go on simplifying this expression so that we can make it into an expression in terms of ZL, Z0, etc. We have got the expression as this. Now we have got a term e raised to gamma L plus e raised to minus gamma L by 2, and here we are having e raised to gamma L minus e raised to minus gamma L by 2. When you consider the expression for hyperbolic sine and hyperbolic cos, sin h gamma L can be written as e raised to gamma L minus e raised to minus gamma L by 2, and cos h gamma L is e raised to gamma L plus e raised to minus gamma L by 2. On incorporating this relation into this equation, we will get Zn is equal to Z0 into VL cos h gamma L plus IL into Z0 sin h gamma L. Here it is sin h gamma L and here it is cos h gamma L. So we'll get this expression. Now we can make it into hyperbolic tan by dividing numerator and denominator by cos h gamma L. So here we have got VL and IL. So VL and IL is there. If you divide VL by IL, we'll get the load impedance ZL. So we'll first divide the numerator and denominator by IL. So we'll get ZL. So Zn will become equal to Z0 into ZL cos h gamma L plus Z0 sin h gamma L divided by ZL sin h gamma L plus Z0 cos h gamma L. In the next step, we'll divide with cos and make it into tan h gamma L. On dividing numerator and denominator by cos h gamma L, we'll get Zn is equal to Z0 into ZL plus Z0 sin h gamma L plus cos h gamma L, and here also the same. So when you divide sin h gamma L by cos h gamma L, it will become tan h gamma L. Hence, the expression for Zn is Z0 into ZL plus Z0 tan h gamma L by ZL tan h gamma L plus Z0. This is the expression for input impedance of a transmission line. So we can do a simplification by considering it as a lossless transmission line. So if we consider it as a lossless transmission line, our expression for gamma reduces to j beta since alpha equal to 0 for a lossless transmission line. So since alpha is 0, gamma is j beta, so this term is tan h of j beta L. So there is an approximation that if tan h gamma L gamma equal to j beta, then it can be approximated as j tan beta L. So the expression for Zn for a lossless transmission line is given by Zn is equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. And this is the expression for input impedance of a lossless transmission line, and here beta is equal to 2 pi by lambda and L is the length of the transmission line. So when you consider a transmission line, if you send a particular electromagnetic wave, once it reaches the load end, some amount of it will get reflected back. So when you consider reflection coefficient, it is a ratio of reflected to incident voltage. That is, we are having an incident wave with its load, and some of it is absorbed by the load and later, but the remaining will be reflected back. So when you consider voltage reflection coefficient, it is a ratio of reflected voltage to incident voltage, and it is represented by capital gamma L, which is the reflection coefficient at the load end. So when you consider the expression for voltage, it was Vs of Z equal to V naught plus e raised to minus gamma Z plus V naught minus e raised to gamma Z. When you consider the load end, the value of Z is equal to L. So it is V naught plus e raised to gamma L plus V naught minus e raised to gamma L. When you consider the first term, it is a wave traveling in the positive direction, that is towards load. So that is the incident wave. When you consider the second term, it is e raised to gamma L, which represents the reflected wave, that is a wave traveling in the negative direction. So if you take the ratio of reflected to incident voltage, we will get the reflection coefficient at the load end. So gamma L equal to reflected by incident, so it is V naught minus e raised to gamma L divided by V naught plus e raised to minus gamma L. On dividing this, it will turn out to be V naught minus by V naught plus e raised to 2 gamma L. Now we need to substitute V naught minus and V naught plus so that we can further simplify this expression. We have already determined V naught minus and V naught plus in terms of VL, IL and Z naught. So V naught plus is VL plus IL Z naught by 2 e raised to gamma L, and V naught minus is VL minus IL Z naught by 2 e raised to minus gamma L. On substituting this back into this expression of reflection coefficient, we will get it as VL minus IL Z naught by 2 e raised to minus gamma L divided by VL plus IL Z naught by 2 e raised to gamma L. When you consider the terms e raised to minus gamma L into e raised to 2 gamma L, it is e raised to gamma L. So this e raised to gamma L, this e raised to gamma L will get cancelled. Hence the expression for gamma L becomes VL minus ILZ naught by VL plus ILZ naught. So this term is equal to 1. On dividing numerator and denominator by IL, we will get it as VL by IL minus Z naught divided by VL by IL plus Z naught. So the reflection coefficient at the load end is given by gamma L is equal to ZL minus Z naught by ZL plus Z naught. So if you know the load impedance and characteristic impedance of the transmission line, we can determine the reflection coefficient at the load end. So when you consider the reflection coefficient at any other point other than the load end, that is at a point which is at a distance L dash from the load, we need to determine the reflection coefficient at the point P. For that, what we are going to do is that we'll determine the distance of point P from the input end. So when you consider the distance of point P from the input end, it will become L minus L dash, since the total length of transmission line is L. So on substituting Z equal to L minus L dash, we will get two terms. One is e raised to 2 gamma L and the other one is e raised to minus 2 gamma L dash. Now when you consider this term, this forms the voltage reflection coefficient at the load end. So the expression reduces to gamma L e raised to minus 2 gamma L dash. That is, if you know the reflection coefficient at the load end, if you multiply it with e raised to minus 2 gamma L dash, we will get the reflection coefficient at any point which is at a distance L dash from the load. Now we have told about voltage reflection coefficient. Next term is current reflection coefficient, which is a ratio of reflected current signal to the incident current signal at the load end. So when you consider the ratio of reflected current to incident current, we need to take the expression for current from transmission line equation, where we got Is of Z equal to I naught plus e raised to minus gamma Z plus I naught minus e raised to gamma Z. On substituting this back into the expression for current reflection coefficient, we will get that we are considering the load end. So the value of Z is L. So the current at the load end is given by I naught plus e raised to minus gamma L plus I naught minus e raised to gamma L, where this is the incident wave and this is a reflected wave. Substituting this into the expression for current reflection coefficient, you will get it as reflected current by incident current. Hence, the expression is I naught minus e raised to gamma L divided by I naught plus e raised to minus gamma L. Hence, this expression reduces to I naught minus by I naught plus e raised to 2 gamma L. So when you consider the expression, it is I naught minus by I naught plus e raised to 2 gamma L. So we can substitute I naught minus and I naught plus in terms of voltage. That is, we know that Z naught is equal to V naught plus by I naught plus, which is equal to minus V naught minus by I naught minus. On substituting this into this expression, we will get it as minus V naught minus by Z naught divided by V naught plus by Z naught into e raised to 2 gamma L. So Z naught will get cancelled. You will get it as minus V naught minus by V naught plus e raised to 2 gamma L. When you observe this expression V naught minus by V naught plus e raised to 2 gamma L, it is same as voltage reflection coefficient. Hence, you will get that the current reflection coefficient is the negative of voltage reflection coefficient. So that is the relation between voltage reflection coefficient and current reflection coefficient. So the next term which we need to consider is the standing wave ratio. So when you consider the incident and reflected wave, it is both traveling along the transmission line. So when these both waves travel along the transmission line, they can constructively or destructively interfere so as to form what is called as a standing wave. Standing wave is something which is stationary and it won't propagate. So when you consider the standing wave ratio, it is actually the ratio of voltage maxima to voltage minima. That is, when you consider the constructive interference, they will combine together, that is thereby adding, and we'll get a maxima. When they destructively interfere, we'll get a minima. So constructive interference will produce a maxima, which is a sum of incident plus reflected, and the destructive interference will produce a minima, which is a difference between incident and reflected. So when you substitute back into the expression for S, it is Vi plus Vr by Vi minus Vr. When you divide the numerator and denominator by incident voltage, we will get it as 1 plus Vr by Vi divided by 1 minus Vr by Vi. When you consider the ratio of reflected to incident voltage, it is our reflection coefficient, which is a ratio of reflected to incident voltage. So this expression turns out to be S equal to 1 plus reflection coefficient at load divided by 1 minus magnitude of reflection coefficient at the load. Now when you consider the range of values which the reflection coefficient can take, the two extreme cases are either no reflection or full reflection. When you consider it as no reflection, the value of reflection coefficient is 0. When you consider as full reflection, incident and reflected will be equal and the reflection coefficient will be equal to 1. So we already told the range of reflection coefficient is between 0 and 1. If the reflection coefficient is between 0 and 1, if it is 0, the standing wave ratio will be 1, and if the reflection coefficient is 1, the standing wave ratio becomes infinity. So the range of values which the standing wave ratio can take is between 1 and infinity. So reflection coefficient and standing wave ratio are the two parameters to analyze between the incident and reflected wave, that is to analyze the standing wave pattern. Now we'll see a question to find input impedance, reflection coefficient and the standing wave ratio. So a lossless transmission line with characteristic impedance of 100 ohm is having a load of 50 plus J200 ohm. We are asked to determine the reflection coefficient, standing wave ratio, load admittance and input impedance at zero point 0.2 lambda from the load as well as reflection coefficient at zero point 0.2 lambda from the load. So with the given values, we can substitute in the expression for reflection coefficient, which is given by gamma L is equal to ZL minus Z0 by ZL plus Z0. So when you substitute the value of ZL and Z0 here, it is 50 plus 200J minus 100 by 50 plus 200J plus 100. So you'll get it as minus 50 plus J200 divided by 150 plus J200. So we'll get the value of reflection coefficient as 0.52 plus 0.64 G. And when you convert it into the polar form, you will get it as 0.8246 angle 50.91 degree, or it is 0.8246 angle 0.89 radians. This is the value of reflection coefficient at the load. Now when you consider the expression for standing wave ratio, it is S equal to 1 plus reflection coefficient by 1 minus reflection coefficient. So here we need to substitute the magnitude, which is 0.8246. So when you substitute the value, you will get 1 plus 0.8246 by 1 minus 0.8446. Hence, the value of standing wave ratio is 10.402. As you can observe, the value of S is greater than 1 and the magnitude of reflection coefficient is less than 1. Now we are going to calculate the load admittance, which is a reciprocal of load impedance. So load admittance YL can be written as 1 by ZL. On substituting ZL equal to 50 plus J200, you will get it as 1 by 50 plus J200, which is 1.18 into 10 raised to minus 3 minus J 4.7 into 10 raised to minus 3 Siemens or mho or ohm inverse. This is the value of load admittance. Now when you're considering the expression for input impedance is Zin equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Beta will be 2 pi by lambda and the length is 0.2 lambda. On substitute the value for Zn, it is 50 plus J200 plus J into 100 tan 2 pi by lambda into 0.2 lambda. Again denominator we will substitute the value. On substituting the values for Zn, you will get the value of Zn as 18.08 minus 93.09 J ohms. This is the value of input impedance Zn and that is at a distance of 0.2 lambda from the load. Now to calculate the reflection coefficient at 0.2 lambda from the load, the expression is gamma L e raised to minus 2 gamma L dash. For a lossless line, gamma is J beta. So this expression reduces to gamma L e raised to minus 2 J beta L dash. Now on substituting the values for gamma L, beta, L dash means it is 0.2 lambda. Substituting that we'll get it as minus 2J 2 pi by lambda into 0.2 lambda. Lambda will get cancelled, so it is gamma L e raised to minus J 0.8 pi. You should substitute the value of gamma L such that the phase is in radians, because here the phase is in radians, so gamma L should be substituted such that the phase is in radians, so it is 0.89 radians. So it is e raised to J 0.89 into e raised to minus J 0.8 pi. So we'll get the value as 0.824 e raised to minus J 1.623. On converting it into the rectangular form, it is minus 0.043 minus J 0.82. Or if you find the phase in degrees, you will get it as minus 93 degrees. So the thing which we can observe is that whatever be the distance we are measuring the reflection coefficient, the magnitude remains the same. Only the phase information of the reflection coefficient will change with distance. So with this, we have come to the end of module 4 of applied electromagnetic theory. In this module, we mainly studied the transmission line parameters, transmission line equations, two special types of transmission line, lossless and distortionless transmission line. Then we derived the expression for input impedance. Then we got the value of reflection coefficient and standing wave ratio. And also we solved the problems based on these expressions. Thank you.